Yesterday we started our discussion on potentiometers. Okay, and I hope that you remember the two-step process of measuring voltage with a potentiometer. First, standardization, next measurement. Standardization means fixing the value of the conversion factor between length and potential. That means how much length correspond to how much potential. Okay, for that we use a standard cell. We put the jockey of the galvanometer at a suitable position wherever we like on the potentiometer wire, and we vary this resistance rheostat to control the potential drop across the wire. After that is done, in the next phase we remove the standard cell and bring in the unknown cell, unknown battery, and then in this phase, in measurement phase, we do not touch this rheostat or this battery again anymore, but we vary the position of this jockey and find the null position, and that position, that length, gives the potential or voltage of or EMF of this unknown cell. One important fact we learned yesterday is that the nice thing about potentiometers is that at balance, since no current flows through the unknown battery or unknown source, internal resistance of the source or the circuit which we are probing does not create any problem or any voltage drop. Today we shall start talking about AC potentiometers. Okay, yesterday we talked about DC measurement. Now today we will talk about AC potentiometer. Okay, to begin this, first thing that I will mention is that the challenge in AC potentiometer based measurement is that there is no standard cell, and what I said so far, that the problem with an AC potentiometer is that there is no standard cell. Okay, there is no source, no AC source which you can take as the standard for measurement. So what do we do? How do we get rid of this problem? We basically use the DC standard cell in an intelligent way to measure AC. Let this be the wire of a potentiometer, and what we will do is this. So it needs a supply, voltage supply. So I will give it two supplies, two alternative supplies. One DC, another AC. And you can connect to either of them. This is to control the voltage or the current through the wire. I will put an ammeter here. The purpose of this ammeter I will tell soon. Okay, now there is definitely some AC voltage that we want to measure, some AC unknown voltage. Let that be here. Okay, call it Vx, unknown, and we need to standardize this wire. for which we need a standard cell. Since there is no AC standard cell, we will use a DC standard cell. DC standard cell. This is the galvanometer to detect null, and of course here I will have the choice to switch between the unknown and the known potential. Okay, the way we will use this is as follows. Please listen carefully. In standardization phase, connect this DC standard cell and connect this DC supply. Okay, now suppose as we did yesterday, suppose this is, for example, let me take the same example, 11 meter long wire, and this potential is 1.08 something, I don't remember. Okay, this is the standard voltage, and suppose we want to measure an unknown voltage whose value is within, say, 1 volt. Okay, then what we can do, we can say choose to have a nice conversion factor, we may choose that 10.8 meter corresponds to 1.08 volt. So we have it now connected to the standard cell. We will put this jockey to this position, and now we will adjust this rheostat R. Okay, and adjust RH rheostat to get null. Okay, at a suitable length, wherever we have put this jockey, at a suitable or chosen length. This is chosen. Okay, this is standardization process. What is important to do here is to note this ammeter reading at null. When you get null deflection, zero deflection, note this ammeter reading. Okay, so, and you remember that reading, don't forget that reading. This is the standardization phase. Next in the
sir, can you scroll down a little bit? Yeah, thank you.
Yeah. Okay, next in the measurement phase, now what to do? Now this we will connect here, because we are going to measure the unknown voltage, and this previously it was connected to DC cell, now we will connect it to the AC supply. Okay, then connect AC supply. Okay, and before you try to get the null, we have to do one more thing, that is adjust this rheostat, to get ammeter reading as before, as it was in the standardization phase. Okay, I said note the ammeter reading and remember that reading. Now after you switch your supply, you adjust this rheostat so that you get back the same ammeter reading. Okay, adjust rheostat to get ammeter reading as it was in standardization phase. Okay. Now, if we do that, if we adjust this rheostat to get the ammeter reading same as before, that ensures now the current flowing through this wire is also as before, as it was flowing at the end of the standardization. That means now if the same amount of current is flowing, that means per unit length there is same amount of voltage drop. What is the difference between the previous voltage drop and now? The difference is that previous voltage was DC, and now the voltage drop is AC. But the value is same. Per unit length voltage drop is same. Previously it was DC voltage, now it is AC voltage. But per unit length voltage is same. Okay? By the way, when I say per unit length voltage is same, I mean it is the RMS value of the voltage. Okay? RMS value of the previous DC voltage is same as the RMS value of, per unit length RMS value of the AC voltage now. Because same amount of current is flowing, same amount of RMS current is flowing. And therefore also it is obvious that this meter that we are using should be an RMS meter. Can it be PMMC?
No, sir.
No. What can it be?
Moving iron.
Good. Moving iron, electrodynamic. Okay.
Electrodynamic.
Yeah. But moving iron I won't suggest, because previously you used it for DC, and we don't like moving iron for DC measurement. So electrodynamic will be better, I guess. Okay, so now same amount of current is flowing as before, so same amount, so now per unit length voltage drop is same as before, RMS value is same as before, and that is known. And now you can connect this unknown voltage, and then you adjust the jockey position to find the null. Okay, so next so connect Vx, unknown voltage you want to measure, and find null by adjusting jockey position. That will give the voltage. Okay, is the idea clear? How we are mitigating the problem that there is no standard AC voltage source. Okay, so since that is okay, clear, do you see any problem in general in this circuit, in this measurement while using AC? Anyone? One problem here is that to get null, it is not enough that this voltage and this voltage match only by their magnitude or RMS value. We also need to match what? The phase angle. Unless these two voltages have same phase, the voltage drop along the wire and this unknown voltage, if they do not have the same phase angle, we will never get balance. That is impossible. Okay, so that is one problem which I didn't talk about. Okay, so this will not work unless we take care of that, or unless these two sources somehow have same phase relationship. Okay, so let's talk about that now. Okay, phase issue. So there are two possible solutions to this. One is like this. Suppose we can control the phase angle of the supply. Suppose there is a knob somewhere, so that we turn the knob and the phase angle of this supply also changes from 0 degree, 90 degree, 180 degree, so on. Okay, then we can also adjust that angle and get the null. So by changing the jockey position, we can change the voltage amplitude or magnitude, and by changing some knob we can change the angle. If that is the case, then that will be very nice. We are done. So let us see whether we can make such an arrangement to change the phase angle of a voltage source, voltage supply, and that is called phase shifter. Okay, we will study the principle, the underlying principle, and we will not go into constructional details for simplicity. Okay, so let me draw two planes. One, suppose this is a horizontal plane, and let me draw another plane perpendicular to it, vertical. Okay, like this. So these are two planes, and now I will imagine two coils. One is in the horizontal plane like this. Say it starts from here, then this is one turn, there may be multiple turns, and let it go out like this. Then I will take another coil in the horizontal plane. Let me start from here. Okay, now suppose I pass two currents in these two coils. Okay, suppose here is one current, call it I Okay, so if current flows in this direction, then in which way the flux will be? Use your right hand rule. It's upwards, right? If current flows, then it will create upwards flux. Please tell me if I am making any mistake anywhere. Okay, so it will create upwards flux if current is flowing in this direction. And similarly, let there be another current, call it Ix, like this. In which way it will create flux? Along positive x direction, I guess. Correct? Okay, so this is the arrangement. Now let me draw a simplified view of this. I will draw only the front view. So from the front view, this green coil, you can only see its cross section like this, and this red coil, you can only see the vertical cross section. This is the front view. Okay, and these flux lines, orange flux lines, due to this red current, will be in this direction, and this flux due to this green coil will be in this direction. Okay. Now suppose these two currents are AC. Okay. Now these two currents, let them be AC. If they are AC, what will happen? This flux, they will also change. So sometimes this flux is upwards, sometimes it will be downwards. Its magnitude will sometimes increase, and then it will decrease, and it will vary with time. In the same way, this orange flux will also change its magnitude with time and also direction if these two currents are AC. Okay. Now let us see what happens if these two currents are not in exact same phase but 90 degree out of phase. So Ix and Iy are 90 degree out of phase. If that is the case, okay, then let me first say draw the two currents. Let Iy be like this and Ix be like this. Okay, and then let us see how the flux, net flux, resultant flux due to these two currents will look like. Okay, so let me draw that at different time instants. So this circle I am drawing here with a smaller size. Okay, now say at time t equal to 0. Okay, this green current is 0, so this upwards flux will be 0. Red current seems negative, so this orange flux will be towards the left direction. So upwards flux is 0 and horizontal flux is in the left direction. So net flux will be in towards the left direction. Do you all see that at time equal to 0 or omega t equal to 0? Next, say we look at it at omega t equal to 90 degree. Then you see that this green flux is positive, green current is positive, so this vertical flux will be upwards, so that will have an upwards component, and the red current is 0, so there won't be any horizontal component, so this will be the net flux. This is at omega t equal to 90 degree. In the same way, you can also think what happens at 45 degree. Okay, so somewhere in between at omega t equal to 45 degree, green current is positive, so vertical flux will be upwards but not the highest magnitude, something smaller, and the red current is negative, so horizontal flux will be towards the left like this. If you take the resultant, if you take vector sum, this will be the resultant flux. Okay, so you see as time elapses, the resultant flux is like it's rotating in clockwise direction as time increases. Okay, do you all see that? Any doubt? So we get a rotating flux. Okay, now after this I will use one more coil. Okay, so let me draw that in blue, And now I will put one more coil. We already have two coils. I will use one more, and this one I will put neither horizontally nor vertically, but at some arbitrary angle. Okay, maybe at an angle like this. Okay, so let the coil be like this. Then it goes from behind and okay, and then like this. So here it will look very ugly, no doubt. So let me draw it in a cleaner way, just the front view. So that will look just like this. Okay, now the two ends of this coil is not given any supply. Rather, we will measure the voltage across these two ends. What do you expect how do you expect the voltage to be between these two ends of this blue coil? Or will there be any voltage at all? Yes.
So will it be sinusoidal?
It will be sinusoidal, it will be AC, of course, because we have a coil and there is a net flux rotating around it. Okay, so therefore we will get an AC voltage induced in this coil, and that will be of course sinusoidal. I mean, at least for this ideal theory it will be sinusoidal. Okay, good. Yeah, but now suppose I change the orientation of this blue coil. I turn it at different angles. I mean, here suppose I move it to a different position. Suppose I bring it to this position. Will we get the same voltage across these two terminals, or there will be any difference?
Sir, means with respect to like the coil is rotating with a particular omega, right? So I think it will be the same voltage because with respect.
Once again, this blue coil is not rotating. It's rotated and
I
fixed.
think with respect to the magnetic field, it's rotating, right?
Right. Absolutely right.
With respect to the magnetic field, it's rotating.
Sir, the voltage will be phase shifted by some angle.
Absolutely right. So both of you are absolutely right. So there is a relative rotation of between the coil and the flux. Okay, so there will be AC voltage no matter at which position it is. Magnitude in this case will remain same, but what will change is the phase angle of the voltage generated between these two terminals. Okay, for example, if I keep it say horizontal, okay, then at time t equal to 0, the flux is rotating like this. Okay, so then these sides will cross the flux at a maximum rate, so we will get maximum EMF at time t equal to 0 if this blue coil is horizontal. But if this blue coil is say vertical, then when will we get maximum voltage induced in that? That will be when this flux is vertical. That means at time omega t equal to 90 degree. Okay, so that means if the coil is vertical, induced EMF will be 90 degree lagging compared to the EMF when the coil was horizontal. So this way,
sir,
yes please.
Sir, if the coil is vertical, then at omega t equal to 90 degree, flux will be zero through it, right? Means the
Flux will be zero, right? Absolutely right. But rate of change of flux will be maximum. You know, I mean, it's like sine, derivative of sine is maximum when the value of sine itself is 0. Okay, so it's like that. so it is the moment when, I mean, this flux is directly crossing this perpendicular conductors. So we can do a thorough more, I mean, if time permits today, I will do a more detailed mathematics, but for now, I think at least the idea is should be clear that this way.
So without doing mathematics, can you explain means why it will be rate of change will be maximum when it is aligning with this coil?
Yes. Okay. Okay. So let me do that. Acha. So suppose here is the coil, vertical. Okay. That means the conductors, I mean, are here, perpendicular to the plane of my board. Okay, so you imagine this is the these are the two sides of the coil. Achha. Now imagine the moment when flux is like this, in this direction. This is magnetic flux. Okay, now if this is and this is turning, so this is turning. Suppose this has turned in delta time, dt time, it has turned from this orientation to this orientation, slight delta t amount of time. Achha. Then how much flux linkage is changed? We can tell it in two different ways. Number one, if this has changed its angle by some small amount, then how much flux linkage is changed? Okay. Flux linkage, okay, what is flux linkage? Flux linkage is basically flux density. If I assume uniform flux density, yeah. If I assume uniform flux density B, then how much flux is going through inside the coil at different angles? Okay, so if it is perpendicular, then the amount of flux that is going through the coil is B multiplied by A. A is the area of the coil which is perpendicular to the plane of board. Okay, but now if let me draw these coils again at a different time. Let this be the flux lines and let the angle between the previous position and the new position be theta. Okay, and the flux density is same. So the flux density is same, but now how much flux is going through this coil? Is it same as BA, or is it less, or is it more?
So less.
It is less.
It will be less. It will be less. And can you also tell me by what factor?
Cos
Theta. Excellent. Because the projected area will be proportional to cos theta. Excellent. So, okay, now you see that now without doing any mathematics, if flux lines have changed their orientation from here to here, how much is the change in the amount of what we call flux linkage? That is the flux that goes through the area is very less. Okay, because almost perpendicular, no, I mean nothing is changing. Okay, so we will get very less EMF induced. But now you consider the other case when the flux lines were like this and moved by a small amount, like this. They should be parallel. My drawing is not. Okay. Now, is there a change in? Is there a significant amount of change in the amount of flux that crosses the plane of coil? Huge amount of change. I mean, because previously, say this is the flux direction. Previously, the flux was going from right side to left side of the coil. Now left side to right side. It has changed the sign completely. Okay, so therefore there is a very fast change of flux linkage. This is one way of seeing that without maths. Another way of seeing this is as follows. EMF induced in any conductor, you can think it is, it depends on, okay, let me, suppose this is a conductor, my pen is a conductor. If this conductor is cutting through flux line, suppose my fingers are flux lines. If my pen is cutting through this conductor, this flux lines, EMF will be induced. So how fast this is cutting these flux lines? Okay, so let them be like this. How fast this is going through those flux lines? That gives the amount of induced EMF. Okay. Now you see, when the flux lines are vertical, then these flux lines all are cutting through this conductor. The conductor is actually perpendicular to the board, and these flux lines are crossing the conductor. So we will get EMF. Okay, when the flux lines are in the same plane of the coil. Okay, we will get maximum EMF. They are cutting the conductors. But consider this blue situation. Okay, when the flux lines are horizontal, if they move by a slight amount, are they cutting these conductors much? Not much. Not much at all. It's like they are gliding by or something like that. So we will get minimum. So does that help you in visualizing this situation, Shubham?
Yes, sir. Yes, sir.
Okay, fine. Thank you. So, okay, this way we have seen that we can create rotating magnetic field, and by changing the position of this blue coil, we can get voltage at with different phase angle. Okay, so this is called a phase shifter. This is just a phase shifter. Now let's go back. What we will do, let me just tell that schematically. Okay, here this was my supply. This is not circuit diagram, and I just want to illustrate you the idea. This is not a way to draw the circuit diagram. Let this be the phase shifter. Okay, so you turn this phase shifter, you change the angle of the supply, and then you use it. Okay, that is the basic idea. Okay, this is don't take it as a formal or a circuit diagram also, not at all. Achha. So now, okay, one other important thing regarding this is that, okay, let me draw the symbol of a phase shifter. So a symbol of a phase shifter is often like a circle, and then we draw two coils, often like this. They are perpendicular to indicate that these are, oh, what's wrong?
Sir, so will our supply be connected to the third coil?
Pardon?
Like, will our supply be connected to the third blue coil which you drew in this diagram?
Yeah, that's what I'm telling now. That's what I'm exactly telling now. Okay. So this is the symbol. It has two coils, that we have drawn in, here in red and green, okay, which needs to get two currents. And yeah, this will work only if these two currents are 90 degree out of phase. Okay, you see here, we have assumed that Ix and Iy to be 90 degree out of phase. Otherwise, we will not get a circular rotating flux. It may become elliptical, changing magnitude, etc. So that need to have same magnitude. These two currents need to have same magnitude and 90 degree out phase difference. Okay, so we have to supply this with two out of phase currents. So what we can do, we can say take a source and then say we connect this coil directly, maybe with a resistance, so that we can change the amount of current. And for the other coil, what we can do, we can, yes,
Sir?
yes.
Sir, means the arrangement of the phase shifter that we use just in that shifter, means in that arrangement, will the net magnitude of the magnetic field be same in all the cases? It will change the net magnetic field B net. So the induced EMF magnitude will change na?
No. I mean, if you see, if we will show that mathematically. If the magnitude of this green and red current is same, then see at time t equal to 0, this horizontal flux will have some magnitude, and at time omega t equal to 90 degree, this vertical flux will again have same magnitude. So therefore the rotating magnetic field will have same magnitude throughout all the time, okay? And therefore now no matter at which position you put this blue coil, because the rotating magnetic field has same magnitude in all the position, induced EMF will have same value. That is also required, and that
Yes, sir.
yeah.
Understood.
Can we
Yeah.
say that
If
like
they are 90 degree out of phase, then the net B net will be same in all the cases.
Yes.
I-
If they are
it's
90
like
degree,
sine square theta plus cos square theta is equals to 1, so that constant would be same.
somewhat
Yes,
like that, somewhat like, yes, absolutely, yes. Yeah, one magnitude is sine square, another is excellent. Yes, absolutely, yes. Okay. So yeah, now here I need to give a supply, a current with 90 degree out of phase. So for that, what I will use a capacitor resistance in series. Okay, let me put it here. Okay, and these are variables. Okay, so I will adjust this capacitor. As I change the capacitance, the phase angle of the current flowing through this coil will also change, and somehow I have to adjust this to make it make them 90 degree out of phase. Okay, that is.
So means why can't we directly means apply connect a inductance or capacitance in series with the voltage source, so that directly you can get out of means phase shifted voltage. So that means this phase shifter then will not be required. We just directly connect an inductance or capacitance.
You mean in this directly give I mean instead of a phase shifter at all, directly put a inductor or a capacitor, right?
Yes, we can take the output from that across the inductor or capacitor, so that the output
Okay.
voltage will be 90.
Okay.
With some magnitude will change, but that we can adjust.
Yeah. Okay. So let me first tell you briefly, then I'll come to that if I go in more detail later. One problem is that when you are searching for the null position in your measurement phase, you will have to change two things simultaneously. One is the jockey position, length of the wire, to account for the magnitude of the voltage, and somehow you also have to change the angle. If we have a phase shifter, there is just a knob that you turn. Basically turning that knob means turning the position of this blue coil, and thereby I mean the angle of turning of this will directly change the phase angle. Okay, but if you put a inductor or a capacitor or something, then and how will you change the angle? First thing, how will you change the angle? And even if you can change the angle, will that make sure that the magnitude of the supply is same? It will be difficult. At least it will be difficult to make that sure. Okay, because you note that in measurement phase, we need to ensure that this current through the wire from the supply is constant. Because if that is constant, then voltage drop per unit length will remain constant, to the amount that we fix during standardization. But if this current is also changing, then that will also be changing, and then we cannot measure this. Okay, that is one thing. We will come back to this maybe again and again. Achha. Next, so this is incomplete, this is yet incomplete. Okay, so two coils got supplied. Now I will draw a third coil at an arbitrary angle, and this will be the output of the phase shifter. Okay, so this is the symbolic representation of a phase shifter. Now when we use this with a potentiometer, what we will do is this. Let me connect it in this way. Okay, and this is turnable. Okay, this third coil is turnable. You can turn the angle. Let me just it will make my life easy if I just name them as AB, and then here I draw everything, I erase everything. Okay, so we connect this to terminal say A and this end to terminal B. So what I mean is that you connect these two ends of the potentiometer in this circuit here. Okay, so therefore here you are getting basically a variable angle fixed magnitude voltage supply. Okay, depending on, so I think we have only 3-4 more minutes, so okay, let me then just tell the procedure. You don't have to remember this procedure. Okay, once you understand, you can do it. The procedure of using this this potentiometer with this phase shifter. By the way, this is called a polar potentiometer. When we use this potentiometer with this phase shifter, it is called polar potentiometer. Polar potentiometer. The name polar comes because, I guess, because the voltage supply that we are getting, you can think it is of the form some V magnitude with theta variable. Okay, as if we are representing this phasor in polar form, and the angle is variable. Maybe that is where the name comes from. Okay, now how to use this in laboratory? First thing we will do is this standardization. Okay, in standardization you connect this to the DC source. Okay, and then you choose where you want to get your null. Basically you first decide upon the conversion factor between length and voltage. Accordingly you put your jockey at that point. This you connect then to the DC source and adjust this rheostat until you get your null at that position, and that means after you get null, your conversion factor is ensured. Whatever conversion factor between length and voltage you wanted, that is ensured. Note down this reading, that is important. Note down this reading. Okay, standardization is over. No, not yet actually. Next you put this to this variable supply. Okay, then okay, you don't need this now. This is steps 2, you can say. Okay, after the conversion factor is decided, you connect it to the variable AC source, and then you adjust this rheostat to get back the same reading as you have noted previously. Okay, so you adjust this, and if you are getting the same reading in the ammeter, that means same current is flowing and per unit length same RMS voltage is there, but it is not complete. Then what you have to do, you have to see this is actually here, this is actually here. Now you have to change this angle. Okay, change this to a different angle. Maybe previously it was at 0 degree, now you change it to 90 degree. When you change it to 90 degree, do you expect, or is it guaranteed that now in this ammeter same amount of current will flow? What do you think? Will it flow or not? Or when will it flow? When will the same amount of current flow through this ammeter even if you are changing this angle? That will happen only if we have a circularly rotating flux. That means these two currents, this current and this current, they are 90 degree out of phase and same magnitude. If that is not so, then we will get an elliptical flux, and when you change the angle of this third coil, voltage will change here, and that will be reflected in this ammeter reading. And then you have to adjust these capacitors, resistors, etc., so that you get back the same ammeter reading as before. That means you get back the same voltage here even if you are rotating it. If that is not happening, then you have to keep changing it until and unless a situation comes when even if you are turning this coil, you are getting the same voltage here. Okay, this you have to do iteratively. Boring, tedious, but that's how the life is. Okay, so that's what we do. And so once that is ensured, that means if you can make sure that even when you are turning this third coil, the knob of this phase shifter, you are getting same voltage here, which means you are getting same ammeter reading here. Your standardization is, your things are now ready. You can move to the measurement phase. Measurement phase means now you connect the unknown source, connect the jockey, and now you move the jockey to adjust the adjust the magnitude of the voltage, and simultaneously here you change the angle by changing the phase shifter position. Find the null, that will give the unknown voltage, and we are done. Yes.
Sir? That means the main objective here is to find the voltage of the unknown AC source, right? So sir, means why don't we directly connect a rectifier circuit with the unknown voltage source and then use the DC potentiometer to find the voltage provided by it? Can't we do that?
Okay, so let me tell this in this way that we can measure same thing in different ways. Yes, what you are saying, that could also be one possible way. But there are many factors depending on which we choose which method to use. Okay, for example, to measure a potential, you can use oscilloscope, you can use multimeter, you can use potentiometer. Which one will you use at different situations? Oscilloscopes, multimeters are easy to use. They will give direct reading. Okay, potentiometer so difficult. Why do you go for potentiometer? The idea is as follows. We can classify all the measurements or measuring instruments in two categories like primary measurement, primary instruments, and secondary measurement, secondary instruments. For example, when you are measuring a voltage or a current using an ammeter, say PMMC meter, that is more secondary measurement. Okay, sorry, let me say it this way. When you are measuring that using a PMMC instrument, that is relatively more primary measurement than when you are using a digital multimeter, say. Why? In a digital multimeter, the principle is more complex, there are more complicated arrangements, and your measurement will be perfect, correct, if all those individual components in a multimeter are perfectly known, everything is perfectly known, only then. But in an PMMC instruments, what are the things you need to know? Only the flux density, only the spring constant, there are less number of things. Okay? So therefore, we will say that this PMMC instrument is more towards primary measurement than a digital multimeter. In fact, a digital multimeter, before it is put for use, must be calibrated against a more simpler, basically simpler or primary instrument like PMMC. Okay, you have to validate that against that, if it is working properly or not. In fact, even PMMC instrument is actually not the absolute primary instrument. Let me tell you about, if you allow me few more minutes, one instrument which we do not normally cover in our syllabus. I don't even remember the name of the instrument. It is called some current balance, named after some scientist. I will tell the name next day. The idea is like this. There we take two long wires, say 1 meter, okay, like this, parallel wires. We pass the unknown current through them in like in this way, okay.
So is this the Kelvin balance?
I don't remember the name, some balance, some current balance anyway. So now if you pass these two currents, okay, then they will repel each other. These two wires will repel each other, and basically there is some arrangement to put some weight. I mean, weight means basically weight, mass on top of one wire, keeping the other wire fixed. Okay, and then you adjust this weight. Basically, some weighing pan is there. On top of that, you put the weight, and you balance this force of repulsion between the two wire with the weight. Okay, and the force of repulsion, that is a function of the two currents, etc., distance, etc. Okay, and distance, weight, everything is more directly measurable. Okay, more easily measurable, and that is an absolute instrument. That is the most primary instrument against which all other instruments to be calibrated. Even when we are talking about a PMMC instrument, you know there is a magnet, and so we need to know the magnetic flux. How do we know the magnetic flux? So for that we have to measure it with some other arrangement. Okay, so that is not a absolute primary instrument. So so there are two issues. One is absolute certainty, another is convenience. If you don't want to rely on too many uncertain things, if you go for digital things, so many diodes, transistors, all are non-linear equipped elements, so many unknown things, very difficult to ensure everything. But this balance is extremely simple. This is used for physicists mostly, so this is called a primary instrument. Okay, but this cannot be used in laboratory or day-to-day use. Impossible. To balance we'll balance it, then we will do calculation, then we will get reading. Impossible to do it in everyday life. But the meters that we get, they are always calibrated against the primary instruments. So their reading is compared with the primary instruments, and after that they are certified for use. Okay, you can read more about it in this textbook, that we have referred in our web page, it is there. Okay, so that's the thing. Potentiometer is like, what do we depend on potentiometer? What are the only things that we depend on when we use a potentiometer? Only we depend on the standard cell and the uniformity of the cross section of the wire. Okay, see, in nowhere we are depending on whether we know this voltage properly or not. We are not depending on whether we know this resistance properly or not. We are not even depending on this ammeter reading, whether this ammeter is giving correct reading or not. Only thing we are depending on is this whether this voltage. So if this voltage is known, everything is known perfectly. In other words, all unknown voltages are calibrated against this unknown voltage. What is the multiplication factor between the unknown and this source? That's what we are measuring. Okay, so that's the idea. What you want to do.
Sir,
Yes.
while finding the null point, how do we make sure that the two voltages are in phase?
Oh, for that, this you have to do iteratively. Okay, so you first move the jockey, find the position where you get minimum deflection. At that position, you change this angle and again reduce this deflection. After that, you may need to again change the position or magnitude slightly. You may have to do it iteratively.
Sir, means when that's we have to means standardize in such a manner that the same current will flow, right? So means when some current will flow through the coil, yeah, it will create its own magnetic field. So in the phase shifter there will be some alterations, na? So means there will be some inaccuracy in the means if current flows then.
In the coil of the phase shifter, you are saying some current is flowing. Okay, acha. So,
Means when current will flow, it will create its own magnetic field that will interfere with the magnetic field in the phase shifter. So the net magnetic field.
which current you are talking about? This current.
So means, yes, sir. In the circuit, the main current means. That current.
Yeah, but you see, at balance, no current is going to be drawn from here. Okay, so that means the situation is same as it was there before you connected this. Before you connected, you have ensured that you are getting a circularly rotating magnetic field, and you are getting the same amount of current here as you decided during the standardization with DC cell. And then at balance, no current is drawn. So that means no loading, no extra current is flowing here, no loading. So same amount of current is now flowing as it was there before. So nothing is changed. Okay.
Okay, sir.
Sir, was that relay current balance?
Yes, absolutely. Thanks. Yes, relay current. Yes, like I was not able to remember that name. Yes, yeah. Thank you. Okay. Anything else today? Okay, then let us stop here. Thank you all for